In this section, we're going to talk about comparing three or more means. Okay, this is also known as one-way analysis of variance, or in short, Anova. Where does that word Anova come from? If you just underline the AN in analysis, the O in of, and the VA in variance, that's Anova. Okay. In a previous section, we compared two population means, and of course that null hypothesis was if the mean of population 1 is equal to the mean of population 2, and of course the alternative would be something either less than, greater than, or not equal to. But now we're going to go ahead and extend this concept of comparing two population means into comparing three or more. Okay, we can have either three or more populations, and we're going to compare if their means are all the same or if they're not. Analysis of variance, or Anova, is an inferential method used to test the equality of three or more population means. Okay, specifically means. And let's go ahead and just go into the requirements of the hypothesis test regarding Anova. First is that there are k simple random samples, one from each of the k populations. Okay, so if we had 4 populations in which you're testing whether the means are the same in each one of these populations, then the k would be 4 in that case. The k samples are independent of each other. That is, the subjects in one group cannot be related to any subjects in the second group. The populations are normally distributed. Okay, so we have to know that they're normally distributed. And also the populations have the same variance. That is, each treatment group has a population variance sigma squared. Now, we don't specifically have to know what that value is. We just need to know that they all essentially have the same spread. Okay, so for example, if just by this picture you can see that over here, the spread seems to be about the same for each of these populations, right? Obviously they're centered at different places here, but the spread is about the same. Okay, so that just means that the variance is the same. Okay. Now, how do you actually verify that? Well, what you do is you take the largest sample standard deviation from those samples, and you just make sure that that's not too large. And what do I mean by that? That it's not more than twice the smallest of the sample standard deviations. And that's really all we need to do in order to show that they have the same variance. So the idea of Anova is, in this particular case, we have k equals 3 populations. We would say in the null hypothesis that mu1 is equal to mu2, which is equal to mu3. And what would the alternative look like in this case? Well, in order to disprove the null hypothesis that they're all the same, we simply just have to show that one of them is different. So at least one population mean is different from the others. So this is like the null hypothesis. You can see that they're all pretty much superimposed on each other. You can imagine that all three of them are actually present right here in this picture. You can't tell that they're all three there because they're completely stacked on top of each other. Okay. In this case, we have this population's mean and the second population's mean and the third population's mean are pretty separate from each other significantly, especially these last two ones. This one is significantly different than this one because of the spread. There's not much overlap. Like right there would be the overlap. There's not much overlap. Okay, so in that case, that would be that at least one of these is different than the others. Now, if data leads to reject the null hypothesis, then we are rejecting the assumption that all the population's means are equal. However, we do not know which or how many are different. Okay, to find this information, we may construct a box plot for each list on the same plot scale to be able to compare them. Okay, what that means is that when we run this test, all we can do is either say that they're all the same or at least one is different, right? It doesn't necessarily pick out which one is different. We would actually have to construct a box plot to have a more visual inspection to see what is actually the population mean that's different than the others. They may all be different from each other. Two of them could be exactly the same still, and then one being off. Again, you would have to construct a box plot, which we'll do in one of these problems to show how to compare. All right, here are the 6 steps for doing a hypothesis test on 3 or more means. Just like we mentioned before, the null hypothesis is going to look something like this, depending on how many populations we're talking about. And the alternative is that at least one of the population means is different. Okay, population means. Step 2 is just identifying the significance level. Step 3, we're going to come with our test stat. You wouldn't really want to do this by hand unless you already had these numbers already summarized for you. It wouldn't be too hard to do this by hand. But if you have data, just raw data, you would probably want your calculator to have a predetermined formula for us to just to choose the list, and then it'll calculate this for us, which it does. Okay. In step 4, we're going to calculate the p-value, which also gives us our test stat. And the function in your calculator, and everybody's calculator should have this, it's just called Anova. And I'll show you where to find that. You're going to click on that, and then you're going to just refer to the list of data. So you're going to have data for this. All right, so it's going to go in like this. You press enter, and you're going to get a test stat. It's going to be an F distribution. And it's also going to pull out a p-value. Again, F distributions have this shape, very similar to the chi-square distribution, starting from 0 and going off to infinity over here. Step 5, just like usual, just make a decision by comparing the p-value to your significance level. And then, of course, step 6, we're going to answer the question of interest in the context of the problem. All right, let's do an example here. Example 1, the following data represent the weight in grams of randomly picked pennies minted at the Denver Mint in 1990, 1995, and 2000. Compute the F statistic for the penny data and test the hypothesis of equal means at a 5% level of significance. Note, the sample data come from normal populations. All right, so let's just run down the conditions here. Do we have random samples? Yeah, they were picked randomly, so yep. Are they independent? Yeah, they were picked. They were created in different years, right? So, and also they were picked randomly, so that also covers independence. Are these populations normally distributed? Well, mostly things that are manufactured tend to be normally distributed, right? There's a target value that they're trying to create these pennies to be, and of course some are a little bit lower than that, some a bit higher than that, and it tends to follow this normal distribution. And of course, he also told us that here. And then the other thing is the largest standard deviation no more than twice the smallest? Okay, so that means we have to actually run our data. Okay, this will be our first list, list 1, list 2, list 3. And just calculate the sample standard deviations just to check for this. Okay, and then we can proceed with the problem. All right, so let's go ahead and put this into the calculator. L1, L2, L3. Okay, we're here at the clear blank home screen. Let's go ahead and put this data into our list. So if we go to Stat, Edit, if you have anything in there, let's go ahead and clear that out. Okay. And let's just go ahead and start typing away. All right, so now that I've entered all the data and I've double checked my inputs, so make sure those inputs are double checked. Then we can go ahead and actually run one var stats for each one of these lists. So let's go ahead and quit out of this. So I can quit. And I'm going to go do stats, calc, one var stat. Let's start with L1 first. And frequency, let's 0. Okay, I'm looking at the sample standard deviation. I see that it's 0.0225. So we just say S1 is 0.0225. Let's do the same thing for S2 and S3. So our data is already in there. We just have to go to stat again, calc, one var stat. Now change that list 1 to list 2. calculate. Again, I'm looking at the sample standard deviation, 0.021, I guess 8 if I'm rounding. Let's go ahead and do that again. Stat, calc, One Var Stats. Let's change that to L3 now. And let's calculate. And what do we get here? 0.0141. All right, so those were our sample standard deviations. And again, we're trying to see if the largest is no more than twice the smallest. So which one was the smallest? Well, this is the smallest. And the largest is up here. So what I'm going to do here is just calculate 2 times the smallest, so 2 times 0.0141, and what do I get here? I get something like 0.0282. Now, is the largest larger than this? No, the largest is actually smaller than that, so that means we're in good shape. It's no more than twice. So what we're saying here is, yeah, these 3 standard deviations roughly have the same standard deviation. The largest isn't extremely larger than the smallest. Okay, so that's what we're saying. We're safe here. Okay, so that means we can proceed with the problem. All right, so again, this is a hypothesis test question. That means there must have been a claim in this question. So let's go ahead and identify that claim and highlight it. It looks like the test the hypothesis of equal means. So they're just saying essentially that the claim is that these 3 populations have the same mean weight. All right, let's go ahead and say that. So we say mu1 is equal to mu2, which is equal to mu3. That is the claim statement. Identify that. And for the alternative, we have to say that at least one of the means is different from the others. Step 2 is our significance level, 0.05. Step 3 is our test stat, right? This is an F test. We're going to be using a thing called Anova in our calculator. And the inputs for Anova are just lists. So since we do have lists, L1, L2, L3, then we're just going to be able to identify those and then calculate this test stat. That output's also going to give us a p-value here for step 4, and we're going to draw the picture. So again, let's go back to the calculator and do that. Okay, we're back at the calculator. Now, I do have those lists in L1, L2, L3. I haven't deleted those yet. Go to stat. We're going to go to test. And I believe for most calculators, if you just go up once, it should be that last one technically. Anova. Just press enter. And it brings you back to the home screen. You see that? There's no like drop down menu or anything like that. So all you have to do is list out all the lists, because you had essentially an unlimited number of lists that you can put in. I believe actually maybe your calculator does limit it to 6. But in reality, if your calculator didn't limit this to 6, this Anova procedure can be done on an unlimited amount of lists, really. So we're going to do second 1 followed by a comma. Where's the comma button? It's above the 7. Then second 2, and then another comma. Second 3. If you had 4 lists, you would keep on going, L4, L5, L6, and so forth. We only had 3 lists, and we're only comparing 3 different population means. So let's go ahead and close this off and press enter. Okay, so the first 2 things at the very top is your test stat, 0.74 is your F, and your p-value is 0.487. Okay, so that's a pretty large p-value, right? So we're not going to be able to reject the null hypothesis. Now the rest of the stuff is a little bit beyond the scope of this course. If you were to take a second part to this class, you would probably explore some of this other stuff. So we're just really interested in the first 2 values. All right, so that was a complete step 3 there. Step 4, we're going to go ahead and draw this again. we do have a skew to the right distribution because it's an F distribution. Starting from 0, we go, has some sort of peak, and it goes on forever here. And 0.74, again, these are all going to be right tail tests. I didn't mention that before, but these are right tail tests. And this test that is in a position along this horizontal axis such that the area to the right of it has to be 0.488. So that's roughly 50%. So to kind of just eyeball it, I would say the 50% mark is probably somewhere around here. Yeah, so that's like 48% roughly. Again, this is a rough sketch. And this shaded area to the right is that p-value. That's a complete step 4 here. Okay. Step 5, we're going to make our decision by comparing the p-value to our significance level. The p-value being 0.488. Significance level is 0.05 from step 2. And p-value is definitely greater than. So again, the p-value represents what? The probability of committing a type 1 error. What's a type 1 error? It's the act of rejecting the null hypothesis when in fact it was actually true. Okay? So if we were to reject that they're all the same and that they are indeed all the same, then there's a 48.8% chance of us being wrong in that decision. So we're not going to take that risk. We're going to fail to reject the null hypothesis. Okay. Step 6, conclusion in the context of the problem. Okay, what was the claim in step 1? Well, all the means are the same. We failed to reject the null hypothesis. So in a way, in quotes, we're still accepting the null hypothesis. So the claim is accepted. Okay, but we don't write it in that way. We're always either rejecting or failing to reject. So there's not sufficient evidence to reject the null hypothesis in this case. So again, we can go through the flowchart to come up with the precise wording for that. Let's go to the flowchart. Okay, here we are at this flowchart. What was the claim? Well, it was a null hypothesis, so we're going to go in this direction. Did we reject the null hypothesis? No, we did not. So they say that there is not sufficient evidence to warrant rejection of the claim that, and they just restate the original claim. Okay, that's our conclusion statement. The last thing here is just more for your information, is to draw box plots on your calculator just to confirm the analytic results that were obtained. Okay, so we're saying that we're failing to reject the null hypothesis. So we're in a way saying that all the means are the same. Okay, so we're saying this is correct, right? That these populations tend to have the same center. Okay, and if we were to draw box plots for each one of these samples, we should be able to confirm that. Okay, so let's go over to the calculator. And the thing is, with the calculator, you can actually graph up to 3 plots at the same time. So it's nice that we have 3. If we had 4 in our problem, then we just won't be able to do it on our calculator. You would have to actually just do 3 at a time. But since we have 3, we're okay. So let's go back to the calculator since I still have my data in there. Okay, here we are at the calculator, and I just wanted to make sure that the data list was right to the side of this. As you can see, we have the 3 sets of data. It's hard to just by inspection, just looking at this, to see if the mean value of each list tends to be about the same, right? It's kind of hard to do that mental math. That's what's so nice about having a calculator that can do all this for you. So let's go ahead and go into stat plot. It's at the very top left. You would have to press second stat plot. And let's go ahead and make sure that all your plots are turned on. So plot 1 is on, plot 2 is on, plot 3 is on. So you have to actually go into each one. Actually, if you just go into the first one, make sure that one's on. And if you just go down to the type of box plot, there's actually 2 types of box plots. One that has little 2 dots next to it. That just means it's going to identify outliers. We don't really need it to identify outliers. We're just going to go to the other one over here. And the list that we're interested in is L1. Okay. Now, if you want to do the exact same thing for L2 and L3, if you go back up here, go to plot 2, that gives us plot 2. Make sure that one's turned on. The type, again, we're going to go to that box plot, and make sure this list is L2 now. Okay. And then go back up, go to plot 3, because you can only do up to 3. Make sure that one's turned on. Let's go to the type here. And then this one's L3. Okay, so mine was already set up like that because I've done this previously. Okay, now from here, you're going to want to completely quit out into the home screen, okay, before we go on. So second quit. And then from the home screen, go to zoom, which is that middle button in that top row of buttons. And from here, we're going to go all the way down to where it says zoom stat. This should be the 9th option here. And I believe that's all you need. Okay, yeah, there we go. There's a couple things I want you to notice here. You notice the very top one, that refers to L1. The second one refers to L2, and the one at the bottom refers to L3. Remember when we calculated the sample standard deviations here? Which one was the largest? Well, S1, right? And you can see how the spread there has a much larger spread than the others. And the third one, the one at the bottom, has the smallest spread, right? The smallest range there. Okay, even though a standard deviation and range aren't the same calculation, but they do measure spread. Okay. And the other thing to note is what we're retesting, that these have essentially the same center. Okay. For the most part, that first one doesn't have a middle box there. I believe that's because there was repeated values. Yeah, I believe there was a repeated value like that. 2.5 was repeated a lot. I think if we just go to trace, we should be able to figure out, yeah, that 2.5 was the median right there. If you go down, the 2.5 for that one is also the median. That seems to be about the center. And over here, 2.495 is pretty. So the centers of each one of these samples were pretty much the same, okay? Or at least there wasn't any evidence to suggest that they were, any one of these was different, okay? And that lines up with our analysis that the center of these samples is about the same. That's the null hypothesis. mu1 equals mu2 equals mu3. All right, let's do another problem. Example 2. Researchers wanted to compare math test scores of students at the end of middle school from different countries. 8 randomly selected students from Canada, Denmark, and the United States were administered the same exam, with the results presented below. A researcher wants to test the claim that the mean test scores from each country are equal. Note, normal probability plots indicate the sample data come from normal populations. Okay. Question here is, test the claim that the mean test scores for each country are the same at a 5% level of significance. Okay, let's go through all the conditions and so forth, just like the previous problem. One thing I do want to note here is, in this particular case, each sample had 8 values, as you can see here. And you notice from the previous example, the sample sizes weren't the same. And they don't have to be. Okay, that's just what I'm trying to get at here. They don't have to be the same sample size. So let's go ahead and go through these conditions. Do we have random samples? Yeah, they're randomly selected. Are they independent? Yeah, I can't see how when you select 8 random people from each one of these populations that they have any relation with each other. No. Normally distributed, they did tell us that they are normally distributed. And then again, we're going to calculate the sample standard deviations for each one of these populations. We're going to go ahead and put Canada in L1, Denmark in L2, and the United States in L3. And let's see what these sample standard deviations are. So let's go to the calculator. Okay, let's go ahead and enter our data. Let's go to Stat, Edit, and let's go ahead and clear out these lists. These are from the last problem. All right, let's go ahead and start typing away here. Okay, now that I've entered all the data here, it's good to take a second glance at it and make sure that you entered everything correctly. Make sure that that's a habit of yours. All right, I'm happy with my inputs there. Again, let's go ahead and calculate the sample standard deviation for each one of these lists by using One Var Stats. So let me go ahead and quit out of this. Stat, calc, One Var Stats. Let's do L1 first. Calculate. I'm looking at the S here. I don't know, let's do like 2 decimal places. So 28.64. All right, let's do the same thing for L2 and L3. Second quit, stat, calc, One Var Stats, L2, calc. All right, I get something like 22.03 when rounded. And then finally L3. I get something like 23.46. All right. Again, we're just trying to see if this data is spread out similarly in each one of these samples. Okay. Sample standard deviations are a measure of spread. Okay. As long as the largest one, which in our case is that first one, that's the largest, and the smallest one aren't too far off. And how are we defining too far off? Well, as long as the largest standard deviation is no more than twice the smallest. So what I'm going to do here is multiply this by 2, which that should be what, like 44.06. And that value is clearly greater than the largest. So yeah, if this largest standard deviation of 28.64 was greater than 44.06, then we would definitely have samples that are too different from each other to actually make a good comparison. Okay, in this case, we can roughly say that each sample has roughly the same spread. Okay, so yeah, that is also satisfied as a condition. All right, so let's continue with the 6-step process here. So step 1 is our hypothesis statements, null hypothesis, alternative. The null hypothesis, well, we're going to need to identify the claim statement. Where was that claim statement? Researcher wants to test the claim that the mean test scores from each of the countries are equal. Okay, so we say that mu1 is equal to mu2, which is equal to mu3, and that actually happens to be the claim. Okay, that they're all the same. You notice that they didn't specify what that mean score is. All we're testing is that they are the same, whatever that number may be. The alternative here, to disprove the null hypothesis, all you have to show is that one of these is not the same as the others. Right, so at least one mean is different. Okay, that's a complete step 1. Step 2, just identify that significance level. I believe they said something about it being 0.05. Yep. Step 3. What do we got here? Well, we have our test stat. Okay, our test stat. Well, to test if all the means are the same, we're using Anova, right? The Anova function here produces a F statistic. Okay, it has a weird, ugly formula to it, which I wouldn't recommend doing by hand. It would take forever. All right, so now that I already have that data into 3 lists, L1, L2, L3, we're just going to go ahead and go to the calculator and come up with this test stat. In addition, it'll give us the p-value in step 4, which we'll need also. when we draw our graph. Okay, here we are at the blank home screen. If I go to stat, go to test, and if I just go up once, we go to Anova. Again, you have to have all your data in there first. And we have L1, so second 1, followed by a comma, which is above the 7. L2, comma, L3, second 3. Close that off, press enter, and we should get a test stat and a p-value. Everything else you can ignore. Test stat is 13.68 if I'm rounding to do decimal places. And the p-value starts with the whole number, so you automatically know that you should draw your eyes all the way to the right because it's in scientific notation, because probabilities cannot be greater than 1. So yeah, this is a small probability, right? So it looks like we're going to reject the null hypothesis in step 5. All right, so let's go ahead and copy over these numbers. Okay, that's a complete step 3 here. This can be expanded. There's not too many decimal places here. Just move that decimal place 4 places to the left, and you'll have this probability, right? It's a very small probability of making an error. Okay, let's go ahead and draw a picture here. Starting from 0. How do I know it's skewed to the right? Well, F distributions and chi-square distributions look like this, and that comes from the test stat. Now, where do I place this 13.68 test stat here? Well, these are always right-tailed tests, so we have to place it in such a way that the area to the right of it is this small probability. So that's a small probability, so this test stat should be pretty far off to the right, 13.68. So that's what this value is. That's a complete step 4. Step 5, let's go ahead and make our decision. How is the decision made? By comparing our p-value to your significance level. The p-value is definitely less whatever alpha was, which in this case is 0.05. So we're going to reject the null hypothesis. It's safe to reject it because the probability of us making that type 1 error is small, so we'll take that chance. It's significantly small. And the conclusion statement, if I can fit it down here, is that, well, the claim was that all the means are different, right? And we reject the null hypothesis, so there is sufficient evidence to reject this the claim that, and then we write the context of the problem. So let's go to the flowchart just to kind of get the precise wording again. The null hypothesis was the claim, so we go in this direction. We actually rejected the null hypothesis, so the wording for our final conclusion is there is sufficient evidence to warrant rejection of the claim that, and then we restate the original claim. And what was that claim statement? Well, if we go back up here, claim that the mean test scores for each country are equal. So we're rejecting them. So that means that they're not equal. Okay, so since we actually made this determination that the mean test scores of all 3 countries are not the same. Okay, we're rejecting that they are the same, so we're saying that they're not the same. Well, how can we tell which country or countries are different from the others? Okay. Well, you can look at the data. Sometimes one just kind of jumps out at you. Maybe just because the data sample size is pretty small. I don't know. I don't see any 400s in Canada or Denmark. I do see them here in the United States, so maybe this is what's driving that the mean test scores in the United States from this sample of 8 people is different from the others, and maybe Canada and Denmark are similar to each other. Maybe they're all completely different. Again, just by analyzing the spread of the data, that's how you actually make the determination, and that's what this test does. Okay. But to kind of get some sort of visual inspection, we want to use a box plot. That way we can verify our results from what our analysis says. So let's go ahead and do that. Our data is already in there, so we're going to do the box plot, just like the previous example. Okay, so one of these countries should be different from the other, or they might be all different from each other. We'll see. Okay, we're here at the clear home screen. If you go to second stat plot, and all my plots are on. Again, you can go through that exercise that I did last time. Make sure they're on, you have the correct type, and the X list is L1, L2, L3. So the first one will be L1. Go to plot 2, make sure that one's L2. Go to plot 3, and then that should be L3, as you can see here. Okay, I'm going to completely quit out of this. Make sure you quit out of this. And then I'm going to go to zoom, which is that middle button in the top row of buttons. Go all the way to the, I believe, the 9th option here. Yeah, zoom stat. Press enter. Okay. I'm also going to press that button trace, which is right next to zoom, to kind of get an idea. And it actually starts you off at the median of each one of these box plots. So the median test score in, I believe, Canada, it was the top one, yep, is 539. If you go down now, the median for Denmark was 562. And the one that was really off was the United States. That one was pretty far off. Okay, median is just a measure of the center. It's not the mean. But this roughly gives you an idea. Again, if we look at the spread, or the range of this, the smallest and the largest value spread of each one of these box plots, which one was the largest spread? Well, it looks like it's that top one, right? Just by the looks of it, it seems like to be the largest. What was the smallest? It's kind of hard to tell from this picture, but from our calculation, on S2 was the smallest, right? And it kind of does look like that. That's the smallest spread there. And like I mentioned before, the United States had about half of them were in the 400 score, so that's why that box plot is far to the left here. It's lower than both Canada and Denmark. Okay, and if you wanted to actually compare if Canada and Denmark are different from each other, you would just do a 2-sample t-test, right, to compare just 2 means, right? And you would do it the same process as you would do in the previous chapters that we dealt with when we're dealing with just 2 populations, right? So the nice thing about this Anova test is that you can compare multiple populations all at the same time. Okay, if there's a claim that they're all the same, it just takes one of them to be off for us to be able to say that the null hypothesis that they're all the same is not correct. But if you're trying to compare just 2 populations to each other, yeah, you wouldn't use Anova. You would just use 2-sample t-tests, right? mu1 equals mu2, and do that comparison. All right, so that looks like it's it for this section. Thanks for watching.